Welcome everyone, and thank you for joining us. Today we are going to be talking about configurable laser welding and how configurable laser plastic welding can save you money. And our presenter today is Nick Flesher, the Director of Engineering here, and he's also the Laser Business Unit Manager. As you can tell, we can use the chat so that we can have a conversation throughout this whole presentation. And if you have questions, that's where you want to put your questions. We'll try to address those kind of as we go along. We might bunch some questions together. And then, of course, we'll have some time at the end for questions if we haven't, answered them along the way. So I think it's time to get started. Nick,
let's roll, Jason.
Take it away.
Hi, everyone. Thank you so very much for giving us some of your valuable time. Right out of the gate, just want you to know we're going to shoot for about 20-ish minutes. If it's really good and we have to cut things off, that's fantastic. We typically see these 30 minutes or less with questions, just so you guys can consume more of them, get on with your busy day. And so as Jason introduced, we're going to talk configurable laser plastic welding and this whole notion that it can save you some money. It might sound a little counterintuitive, perhaps, but hopefully when you get into this, you'll learn that we've got some approaches that can actually do some unique things with laser plastic welding. Just a couple of quick comments. We're going to focus a little bit on more of a solutions approach. If you're looking for more theory-based, we have on laser plastic welding, we have some webinars that we've done in the past that you can go to our website. We'll send a link out after this webinar is done, and you can learn about the basics. I think we did one called Myths of Laser Plastic Welding, which was helpful to some folks. Designing for laser plastic welding. And then secondly, in addition to those basics, if you want to talk about a specific application, of course, we're here for that. We love that stuff. This will be short time frame. So if you want to reach out to us afterwards, we have a full applications team that looks at all plastic welding, plastic assembly challenges. So with that introduction out of the way, let's go ahead and get going. First thing we want to do, just 3 or 4 slides here to talk about some just high level basics, just so if you've never been exposed to it as you guys engage in the chat, which, by the way, I think we're going to have a good group, Jason. Some folks are already engaging, which is great. And we'll try to answer those real time. But just a few basics before we get into this whole notion of configurable plastic welding. The process itself is a 3-step process. It's simple. It's clamping, it's heating via laser, and it's cooling. So at a face value, that's the process. Really straightforward. There's obviously process parameters that go from there, but that's the laser plastic welding process. We'll talk through a few basics, just a couple slides on the basics of application method, and the first and foremost is what wavelength are we using? We use 2 wavelengths, 1 micron or 980 nanometers, very specific wavelength, which is for transmissive welding, which absorbs into a lower. I'll talk more about in a moment. And then clear to clear, 2 micron or 1940 nanometers. There's different ways that is applied, and there's different nuances to it, but for obvious reasons, we can't go into that now. You can check out those earlier webinars or reach out and we'll give you more information on that. But we absolutely want to talk about 3 key elements to laser plastic welding. The first, and I won't say the most important because they're all important, but definitely something we see is crucial, is intimate contact. We throw that phrase around a lot here. It essentially means that you have to have uniform, really good close contact so that the method of, especially the 1 micron laser welding, works with conduction. That's what's really key. We're actually transmitting through an upper component, absorbing into a lower component, and conducting that energy into the upper and lower. It's really precise. But that's why you need that intimate contact. And that happens primarily with tooling, the right force parameters. And so that's really, really crucial. I already touched a little bit on the second one, IR transmissivity and absorptivity. We definitely see that the material content of both of those 2 things really, really matter. And it shows up as process window, weld quality, and cycle time as far as welding goes. And then compatible materials. Just like any welding technology, you have to have compatible materials. And we've got some compatibility charts on our website. You can check into that if you have questions on dissimilar materials and so on. So what makes laser plastic welding expensive, or what can make it a little more expensive than what you need? The first and foremost, a lot of companies, in fact, I would say most that do laser plastic welding, try to fit customers into a standard welding machine, standard size welder. That really means that maybe you might fit, but maybe not, and then you're going to get upsized, or there's different types of welding technologies that maybe aren't accounted for that might not be the best solution. Second would be if you've got a standard machine, it might be expensive. If you have some existing additional features that you might want, or some additional functionality, it might be more expensive to add those features to a standard welding machine at another company. Other assembly functions might require additional equipment. This, frankly, is what we see probably 80 to 90% of the time with our pieces of equipment that we sell. Companies looking for maybe a little more functionality than I just need to weld plastic parts. Of course, we have to do that well, but we've in some cases eliminated 2 or 3 other machines in addition to, or rather consolidated 2 or 3 machines into one machine using the approach of configurable laser plastic welding. Laser welding is expensive if it's not the right technology for your application. Let's just park on this one for a second, because a lot of suppliers, laser welding suppliers, that's what they do. They do it well, but that's all they do. And so if you don't need that solution, you don't need, I saw someone in the chat talk about vibration welding or ultrasonic welding. If that's the right approach and the budget, and maybe you don't need clean parts warrants that, absolutely. It's realistic to go into another technology. So through our applications lab, we say, let's not just take let's do laser plastic welding approach, but we try to find the right solution for the right problem. And I think definitely you just shouldn't pay for technology that you don't need. So the last point here is definitely something to be expanded upon: lack of understanding of how laser plastic welding, what the best methods are. There's two main points to make here. We have seen companies that it's not a core technology for them. Maybe they're custom house and they've bought an off-the-shelf laser. We've seen poor quality welds that we've actually helped to fix tooling, fix process parameters, actually add some measurement and quality assessments. So there's more to this, but just generally they might not know the best way to do it. And then another thing we've seen is a lack of understanding based on power and cycle time requirements and welding methodologies. I'll talk more about that in a minute, but expensive is all relative, right? Like, how much cycle time do you need? How much is it going to springboard into more machines? Can you keep run at rates? And so we look at the total need and say, boy, what's the best requirement that machine needs to fill? So this one's huge. We've actually seen companies that have written laser plastic welding off because cycle times have been really long, or the process window wasn't as wide as what we certainly have seen that it should or could be. So let's talk about this word, configurable. What this webinar hopefully has gotten most of you here. What's a configurable approach to laser plastic welding? You can kind of see two images to the right there, hopefully. And I'm doing a lot of talking. We think
we're good. If you guys have questions, go ahead and pop them in. But I think we're doing good right now.
Okay, awesome. So what you see on the left is more of a simple, straightforward approach the customer needed. And then on the right, more of an automation approach. And essentially, a configurable approach to laser plastic welding it's an application-specific approach. What do you need, from just getting the parts to weld really well with a wide process window to what manufacturing process you might have? So we look at laser types when we talk about configurable, machine styles, manufacturing methods, additional operations, which I touched on a little bit with going from 2 and 3 machines down to 1, part handling requirements, upstream and downstream inspection. So just at the simplest answer, what's the application need? And then we take an equipment approach to it, where I think in the market, and we've gotten a lot of feedback that it's kind of inverted. This is the equipment that we've got. how we're going to get your parts in it and what tools you need. We'll tell you what tools you need. So just a few screenshots just to put a little visual to it. Obviously, there's more than this out there that we've looked at, but on the left, the drawer slide, a customer really said, I want you to design this for a drawer slide. Their cycle time didn't need to be any faster than that, and that was best for their ergonomics. The middle machine is a pretty slick approach we had with a dial so that an operator could load and unload while the laser was doing its work, eliminating about 10 to 15 seconds. You want to talk about cost. If that's eliminating 10 to 15 seconds, that might eliminate an operator or eliminate another machine. And this particular customer had some requirements on light curtains that we considered. There's an inspection. You can kind of see it's a little bit small, but there's a little bit of a inspection vision system there. And this is a 2-up. We've done different configurations of this. And then on the right, again, more straightforward approach to a piece of equipment using modules and start models. So you might be asking, well, how do you arrive at the right solution? Cycle time, budget, and auxiliary functions are kind of the three main points that we look at. Power shows up in both of these two, cycle time and budget, of course. Power is kind of an interesting, and we'll talk about the methodology of welding in a minute, quasi-simultaneous or contour. But we look at the best laser application and we say, what power do you actually need and what cycle time typically? So, with power, it could be, and actually I think I have this on a slide a little bit later, but we have a pretty big range that we select. Automation and equipment requirements such as pick in places, through conveyors or dials, as I showed a little bit earlier. Tool features such as maybe a part eject or maybe some locating features with some tool action. Multiple laser sources definitely should be considered. Most of what we do is one laser source, so it keeps the cost down. There's welding technology that has multiple laser sources, but this is more like 1, 2, or 3. Budget, tool complexity, power, small part builds is actually separate, but those two main points, tool complexity and power, really can feed into the budget, which we'll get to in just a minute. And then I want to mention small part builds because as far as the right solution goes, we found that a lot of customers aren't ready for capital. And through our process development center, we can do part builds in the 1 to 2,000 part range, up to the tens of thousands of parts. And so by doing that, you're really sort of refining your weld geometry, you're validating the weld process, and you're using our capital to do it. We've got lab equipment that can help with that. So, that budget, we really find that people use quite often. They're not ready to invest the capital in even production tooling.
Good question. So is this laser welding technology only available for a fixed environment? Because David says that they do a lot of robotic ultrasonic welding, and he's wondering if they can be packaged and mounted to a robot.
Packaged and mounted to a robot, I would say, is trickier than it would be ultrasonics by far, because those three key elements, intimate contact is really, really crucial. We have used lasers on robotic cells that really more are for like the tools actually integrated. And so you have to do some auxiliary clamping. Is it possible? We probably would need to explore that further, look at part geometries and maybe cycle times, because that would be a slower approach. So probably a lower volume approach. And the biggest thing is, how do you make sure that you're clamping and getting good intimate contact? It's not necessarily like metallic laser welding where you can get the two parts closer together and you have to apply the force to it.
David, are you talking about spot welding with ultrasonics? And is that how you would be wanting to use laser for like welding spots, or are you thinking more of like a linear weld of the perimeter of a part or something like that? I'm curious because, contour welding, you'd have to have a tool that holds the entire part in intimate contact, but then you could have the laser source moving along on a robot, right?
Yeah, there's XY gantry, there's laser source moving on robots, but I think the key is, when I think of in terms of Comparing it to ultrasonics, spot welding is kind of a good question to ask. I think it makes it a little trickier. Is it feasible? Absolutely, it's feasible. And using the scanner is another thing. Moving the scanner rather is another thing we've done where we'll need 2 scanners and maybe there's enough cycle time. But I think it really gets probably deeper into the application. I just saw door panels, I think, in the question. So we probably should take that one offline because that's intriguing. I think it's possible. It's not as common as what we typically see, is what I would say.
And it sounds like he said welding hollow bosses on door pads, which to me sounds like plastic staking. So, this is really not appropriate for staking.
No, that's right. Yeah, this is more for welding the 2 materials. That's a good point. Good question. I think especially with high content, a lot of bosses, a laser really isn't going to give you a benefit. We have a couple other options, and ultrasonic obviously works really well and is cost effective on a robot. So,
okay,
good question. Yeah, good question.
So auxiliary functions.
Yeah, auxiliary functions. So arriving at the right solution, and we find that this is just something that customers might not even think about, and so we bring this up, not necessarily in our process development center or apps lab, but in our manufacturing solutions center, our MSC. We've got some manufacturing engineers that quote and look at the whole entire manufacturing needs. But part mark, just to name a few auxiliary functions we find in our machines, either we suggest or customers come to us on: part marking, leak checking after the weld is complete. You do have to be mindful of temperature on that. But I will also say that laser welding is really precise, and so we don't get excess energy into the part versus other methodologies. It does get hot, but not like a hot plate welding or certainly a vibration welding.
The weld gets hot, but not the part.
Right, that's right. Yeah, super located, super local. Vision inspection, both pre and post. So for installation versus post weld, both options. Short shot detection, continuity checks. If you've got an electrical component with a quick connect on the back, barcode printing or scanning, multiple cavity nesting, and compression limiter insertion, all just to name a few. And so therefore you can really sort of, that's the key to the whole subject of how configurable laser plastic welding can save you money. So this is an image of a configuration that we've done on the right, and is a 2-up. Just before I get into the bullet points, this is a 2-up press. We're doing 2 parts here, and this was a great example of a company who was thinking they needed 1 laser plastic welder, but we're using 1 laser source. This is the scanner that you see. Some of the optics, the rest of the optics are not visible here. But I want to say that we're running 2 parts every 25 seconds with this setup.
And this doesn't show the safety enclosure.
No, right. Yeah, this is bendy contents, so we can just show a little more detail about what's happening with the setup. So the safety enclosure, I went ahead a little bit. Safety enclosure is definitely something we look at. You obviously saw different setups in the 3 examples we showed. If you're using a dial, you don't need a large press motion, and a safety enclosure looks very different. And that designer did a slick job of making sure that he could enclose the laser space by the tooling. He used the tooling itself to do that. So we do have a laser safety officer on site. We do a full inspection, post manufacturing, getting it ready to ship, inspection, and then also we file the FDA reports required for that. Press assembly is a big one. I think this really is probably part of the biggest thing we see with configurations for pneumatics, being the most cost-effective way to do it. We do a multiple stage force approach with pneumatics, and so we're sort of chasing the weld while we advance while we're putting energy into it, and is a good cost-effective way to do it. And I'll also add, if a company doesn't need the sorry, I saw a question that distracted me there. What was that question?
Can we replace the heat seal welding to laser welding? So if you're doing heat sealing, can you use a laser welder to?
We have tried that. I would absolutely say we should try it for your application. There are ways that works well. We still have to contact the part to do like an embedding. I'm assuming like it's a film embedding type of process. And so we've done some applications work on that. We haven't rolled anything like that on production yet, but yeah. So I was saying that from a pneumatic standpoint, that's just most of what we see and what we do with a multiple stage force approach on that. And we've had companies that have done applications work that only need 50 pounds, and that saves them a whole lot of money. If that's all you need, we designed the tooling and the machine around that. If you need a really fast cycle time, servos definitely the way to go. Adds some cost. Hydraulics, if you need a hydraulic press, you need to get the forces up there. Definitely also adds some cost. And then, as I said, size of the application. Clamp structure is just the mating piece that goes with the press assembly, and that can either save you or cost you some more money. And then I want to park on laser source a little bit. We have seen where 25 watts gets a customer a 2-second laser on time because their parts are really small. They've got a really absorptive lower component and a really transmissive upper component. So you don't need much power. We've seen customers that have 2.5 millimeters of glass-filled nylon, and we need 600 watts, 700 watts to make sure we're hitting cycle time. Usually not past 700 watts. We can get more than that, but that's not usually something that we typically see or the industry sees for sources. And from a cost standpoint, just to give you guys a little bit of a feel for that, we can use a 25 watt system in a very basic setup in the 150-ish to 175-ish range. And then usually those higher powers can increase costs in the 25% range and above. So up to 50% actually I've seen. I'll just kind of talk about this for scanners, the language that we use with the one laser beam and tracing around a part. Normally a 2-dimensional scanner works just fine for a relatively flat and approximately 12 inches or smaller setup. We can go up to, I think, around 16 inches by 16 inches. If you need to go larger than that, or there's some adjustment in the Z direction, you may need to look at multiple laser sources or a 3-dimensional scanner, which can drive the cost up 25+% on the whole system, the system as a whole. And then the optical lens packages, I won't go into too much detail on this. We look at that in a couple different spots of the system, but we look at the lowest cost approach for what the customer needs for that as well. Tooling, I've mentioned tooling on at least a couple occasions in this 20 minutes. I said I'd go 20 minutes. I'm at 22.
We're going to hurry up.
I know. Quick change is something customers can ask for. What's interesting about quick change versus dedicated. Dedicated is a great approach for a lower cost setup that you're never going to change out for maybe a life of a product, or you don't foresee that. Quick change though, because if we size the system appropriately to run really fast cycle times, we can eliminate a second welder. We have done that before, where we have 3 tools that we sell with 1 machine, and the company can use the right amount of operators and the right amount of assembly time to just have the 1 welder. Progressive is something that's also just noteworthy, where you might need to weld 2 different components, but one subassembly goes into the second weld. That can sometimes help out. We have Greg asking about
the optical scanner is to confirm the part is within spec prior to the weld. No,
good question. The optical scanner is to move and manipulate the laser beam. It is we run the laser path through that scanner. So there's a single laser source fiber optic coming in. It's manipulated with some lenses, goes into the scanner, which then moves the laser beam. So there's typically, we had a question about robotics. Glad you asked that, Greg. Typically, the scanner is, I won't say typically, it's fixed, mounted, and that's what's moving the laser beam around.
And that's that orange thing in the picture.
That
right?
is the kind of
the gray box.
The gray box. This is a special lens that we use. This gray box here is the scanner, and can move the laser beam up to, I think, 4,000 millimeters per second. So you get some really, so fast that if you use a red pilot beam to line it up, it doesn't look like a point, like my pointer. It looks more actually like my pointer moving.
Like a line.
Look at that. I didn't even plan that, Jason.
That's pretty good.
All right, so we've got about 5 minutes left. Control system wise, obviously we can do whatever specs are needed by our customers. Only a slide or two more. Quasi simultaneous, I mentioned earlier, as many fast passes along the weld path simultaneously displaces the material. The contour welding, mentioned a robot earlier, XY gantry. Larger parts typically is one continuous path. You'll notice here that you've welded the part. At some point that beam spot has to get around there. So this is an area that you have to watch for if you use that welding technology. Line beam is just to sort of showcase we can do some different things with optics, and these are good for larger parts, microfluidics, other kinds of devices that don't have a defined weld path. And then masking for really small, ultra precise weld ribs, less than typically 0.7 millimeters. Just want to touch on really quickly, we've got other technologies at Extol, and custom automation is absolutely something we do probably more of than anything else. Hot plate welding through our rapid conductor. If you're not familiar with that product, I highly encourage you to check it out. It's for people who maybe have written hot plate welding off. A couple different proprietary staking technologies: InfraStake, which uses infrared staking, and NanoStake, which is a patented device for us. We talked a little bit about laser welding, obviously, here today. Spin welding. We've got a 3D printing department, our digital development center, which uses multi-jet fusion from HP, and InfraGuide, which is an IR contact, non-contact welding process. It's a little different than what has been used out in the market. So with that, we focused heavily on the configure portion of this in this webinar. Collaboration and design is something we are eager to do with you. And then all the way out into production, we've got a full service department that helps with equipment for the life of the product. So
Questions?
Jason, am I missing anything?
I don't think so. I think
All right.
you made it pretty clear that you have standard laser weld manufacturers out there that have a box and they're trying to put your part into that box, and
Nobody wants to be put in a box.
and we have the approach of we take your part and we build a solution around it. So
Any other questions? I don't see any questions at this time.
So I want to remind everybody that I'm going to take a second and we'll take this recording and the PDF of the slides, and we'll be sending that out via email afterwards. It'll either be later this afternoon or tomorrow when you get that. Looks like, oh, we just got some questions.
Yeah.
So is annealing required with laser welding? From Paul.
No. I mean, I suppose that question might be valid if your parts are really warped. I'm assuming that's where that's coming from, which it's plastic, parts get warped. If we do clamp them into flatness, they have to be for laser plastic welding to work. And typically we see that there's no post processing needed for that. I'll say typically because I haven't seen it yet.
Okay.
So
Justin asked, what are the pros and cons of the different weld paths?
yeah, good question. If we can use quasi simultaneous, we do it. We get a better weld quality typically that way. It's faster. You might need more wattage to do that. But if the parts are geometrically right for that, and that's a longer answer, but I'll just say generally flat and generally under 16 inches by 16 inches. Quasi simultaneous is probably the better way to go. If there's other constraints that maybe we're not talking about or highlighting here, contour may be an acceptable path. We've gone back and forth with line beam in a few applications. Again, the microfluidic space uses that quite often, but mainly it's quasi simultaneous for us.
Greg asked, do you have flatness or profile requirements, or does clamping overcome this?
Most of the time, clamping overcomes it. The laser plastic welding is not like vibration welding, I would say, as to it can overcome and you're just forcing that part into submission. You have to have that intimate contact. And we'll do that with some tooling and obviously force. As far as requirements, I would say it depends on the part. Meaning if it's a 12-inch by 12-inch part, we could probably clamp that into submission and get it to have the intimate contact we need. If it's a smaller part, thick walls, and it just is 80 thou or 3 or 4 millimeters out of flatness, we're gonna have a hard time with that.
Mm-hmm.
Yep.
What is upward and downward inspection mentioned earlier in the slide? Oh yeah.
Yeah. So
where did we say that? This one. Yes. Upstream and downstream inspection.
upstream or downstream of the machine. Good call.
So before welding or after welding, we can inspect the part.
That's right. Yeah, that's right. So that could be part inspection. I mentioned short shots in one previous slide. With that obviously in the plastic space can be an issue. So it could be as simple as what you would typically do in a machine like Extol would build with outside of laser plastic welding. It might be more specific. We've got an application that's got a really hard, difficult load going through the shop right now, and so we had to spec a Envision system that could check for the installation by the operator, and then we're actually checking the weld quality with that same system.
Right.
So this one's got a little weird. Typically we check a quality inspection. We use is collapse, weld collapse or displacement of the part. In this particular case, it's a part that's not a great requirement, and so we're doing a visual inspection to catch like gross misses and things like that.
Does the weld need to be planar, or can you weld contours?
We can weld contours. We do have to consider refraction. I mean, if you go back to your physics and optics classes, there's a point where the laser beam can bounce off the top of the part. We typically see that. You're testing my technical piece. Our application engineers know that off the top of their head. I think it's 15 to 20 degrees. And so we've looked at 2 scanners, 2 sources for that. If you have a curved part, I think there's actually an application going through that's 3 locations. It's a very curved part. So multiple scanners can overcome that. And the 2D and the 3D scanner can overcome that. Yeah. So if you've got a lot of height differences for the more straightforward applications, are like a 1/2 inch, 3/4 of an inch of Z height change, you can't do more. It's just.
Can you explain the difference between 2D and 3D? I think some people might not totally understand what 3D really does.
Yeah, 3D. Yeah, really good question. Three-dimensional optical scanner means that we're actually adjusting the focal point dynamically while we trace the part. So we will adjust the focus of the laser beam, because if you're out of focus, you don't get the focus energy that you need. You might need more power to overcome that. Typical beam spots are 1 to 5 millimeter, roughly. That's a big range, but we've used all within that range. And so you have to maintain that same focal point throughout the trace of the part. And so if the part's got, say, like a 2-inch ball in it and a little bit of angle, and you don't have refraction, and everything's all, working copacetic, I would say the best way to describe it is it adjusts the focal point as the scanner hits that lower point.
Okay. Yeah, makes sense.
Oh, that makes sense.
And so Paul asked, what is the average weld speed in millimeters per second?
For contour welding, I would say it's all over the place. As fast as the motion can take you, because it's XY gantry or robot in that state.
Yep.
For quasi-simultaneous, it could be as low as, it's as fast as we can make it, basically. Because that means you're uniformly displacing, melting the plastic. So if you're on a budget and you're like, I'm only going to buy a system that's 50 watts, you're going to be limited by speed. Usually we start at probably 1,000 millimeters per second. I would say most of them are in the 2,000 to 3,000 millimeters per second range.
That's
when it's all said and done.
Yeah.
Yeah.
What are the smallest spot sizes that you can achieve a good weld without a mask? So,
all right.
Yeah.
I would say 1. Our little slider says 0.7. I would say 1 millimeter. And I also would say at that point, then you're talking about making sure you've got dimensional stability in your part. And we can work some of that out in tooling. We can't work all of it out in tooling. Here's an example. We had an application where the tooling was doing its job, but the part was bowed inward a little bit. And so we don't consider that weld rib is considered in that sort of situation. So we have to make sure we've got the right beam spot. We could do some tricks with the scanner where we'll run multiple paths over the same part to increase process window.
Yeah.
Yeah, but usually it's around one. It's a long answer for one. Just said one.
We got David said good information, and he was commenting on the other technologies that they're looking into. So yeah, thanks, David. And Ken says thank you as well.
You're welcome.
We are 5 minutes over time, so if you guys need to drop off, that's totally fine. But if you have more questions, feel free to drop them in there. If you do happen to leave but still have questions, you can send us an email or just reply to when we send out the recording. You can just send an email back to that and we'll get in touch. And if any of you, I'll turn the camera to me. I'm missing valuable screen time.
Yeah, you need your screen time.
If any of you really want, if you guys want us to come in and do laser training for your company specifically, and you can get all your colleagues in the same room because you think that this would be valuable for them, we are open to that. So let us know if you want us to come in, do a training. It can be very specific on design. It could be general on just the basics of laser welding, or it could be looking at specific applications. Any type of training or discussion that you guys want to have, we're open to that, and we would welcome the opportunity to come in and help you with whatever you're dealing with.
Jason, I see a question there. Someone would like to know what the round number is of base machine.
Oh yes.
So
yes.
I'm happy to answer that question.
Yes.
We typically, I would say the normal range that we suggest would be about 175,000 to 250, depending on like high power systems. But I'll also say that we've had customers that don't need that, and we have hit, I think, 150 for a base before. Definitely, I mean, so to that I have to say, laser welding is the right solution if you need fast, clean, precise, visually aesthetic welds. Ultrasonic is definitely a viable option. We bump up against that sometimes, and it goes both ways. We'll get them in and we'll say, we're not going to sell you a laser welding machine because you don't need it. You're not saying that this has ultra clean requirements and things like that. So that's a bigger number when you compare it and contrast it against those kinds of machines. But this webinar is really important to try to understand that number might just be multiple machines in one. So whereby you might be looking at vibration welding is definitely out there as a high adopted technology. Those machines might be in the 120,000 range. Do you have a clean out station afterwards? Because if you've ever dealt with a clean out station, they're typically not 100%. They do a good job, but they might not hit your internal cleanliness requirements. If you're in the medical or consumer product space, it's got to be worth it. I mean, that's definitely something we're straightforward about at Extol.
So Abe, I'm wondering if you can rephrase your question, because I don't totally understand what you're asking. I'll read it to Nick here. If we have new application, is this machine applicable to the new one? I'm not sure.
I think maybe you're suggesting could we tool it for a second part, or you buy the machine, give us a nod maybe if that's the right thing. Absolutely, 100%. In fact, I would say that there was a laser welding technology that was floated out there a number of years ago that was slick at the time. I think the patent might be coming up on that one. And that was an expensive setup with a very expensive tool. This goes the other way. This is a super flexible, quasi-simultaneous laser plastic welding. It's a mouthful. Say that too fast. Mm-hmm. The systems we've talked about here are adjustable, literally recipe specific. If you've got 3, 4, 5 tools, we dial those in, you take the tool out, tool ID, new tool in, you're making parts less than 5 minutes later. All goes into the cost analysis, right? Like, if you're doing a larger part for ultrasonic, and those horns might be expensive and hard to tune, and you've got multiples of those, this might be at the end of the day, a better cost-effective path. So expense takes on different forms, right? Great questions, you guys. Really appreciate it.
Well, thank you all for joining us. I think we'll probably close it out here. Like I said, if you have any other questions or you'd like us to come in, just let us know. And have a great afternoon. Thanks.